This is the picture of how the foundation pillars are placed in the Antwerp porthouse. As the upper steel structure had to be built above the existing building without affecting it, foundation construction took place in the courtyard of the existing fire station and outside the building where new underground parking lot is constructed. The construction of the underground parking lot and the core foundation have been processed at the same time. This leads to an extension of the concrete pillars deep down to resist lateral load from strong wind currents and heavy loads from the main structure. Reinforced concrete pillars were used on the foundation work. After drilling the hole down the ground with the tube pile, steel reinforcements were placed into the tube with adding concrete. After the reinforcement concrete hardens, tube extraction took place. The reinforced concrete pillars were deeply placed into the high-density ground level to maximize the friction force to be able to withstand the load that is over 1,500 tons. Instead of only placing vertical pillars, inclined pillars were also used in the foundation. The reason is because of the higher resistance it has from their axile capacity. Compared to vertical piles, inclined piles generally have higher horizontal stiffness, mainly due to the fact that inclined piles provide partial horizontal resistance from the axile capacity, and the axile stiffness due to the pile-soil interaction is normally higher than that along the lateral pile direction. After multiple reinforced concrete pillars are placed into the foundation, pile cap is placed on top of the pillars. Pile caps create a stable foundation and offer a larger area for the distribution of the building load onto the piles. They act in a similar way to piled raft foundations where a concrete slab rests on soil, which may be susceptible to movement above a group of piles.
From now on, I will talk about the column of the Antwerp porthouse. As you know from many other examples, Zaha Hadid had a great preference for white, exposed concrete and complicated shape in the design. And when she designed various components of the Antwerp porthouse, that preference was reflected in the column. The thick and big, non-cubic shaped column of the porthouse is considered as a good design, which reminds people of the image of a boat splitting the water. But the design also made the engineers worry about some problems. Since there was a little space for the columns in the site considering the existing building, heavy superstructures need to be supported by limited infrastructures. And complicated 12 lateral surfaces at different angles would be beautiful, but proceed to make it would not be as beautiful as we think. To solve these problems, Interbuild, the company in charge of construction, selected Doka for each formwork solution. Doka use SSC, which is known as self-compacting concrete or self-considerating concrete. It is a special type of concrete which can be placed and considerated under its own weight without any vibration effort due to its excellent deformability. And despite of the fluidity, it is also cohesive enough to be handled without segment or bleeding because of various binder contents. With this concrete, workers can easily pump concrete into the mold with few workers, and it was appropriate for tall, non-cubic column which Antwerp port house had. And SSC generally considered to have higher strength compared to the traditional concrete. Less hole or bleeding means durable structure. And if they build the column with normal concrete, they need to be very careful for an external compaction issues in thick structure, which would be no problem for SSC. Furthermore, reduced finishing requirements, which is important for exposed concrete structure, and less noise due to skip of vibrating was another advantage of SSC. Due to the shape and the white SSC, the formwork had to withstand enormous concrete pressure of up to 100 kPa. These requirements present specific formwork engineering challenge during construction. Doka formwork experts divided the 22-meter high column into 5 segments ranging from 3.7 to 5.5 meter in height. A custom 3D model of the formwork concept, meeting all requirements, including form tie and joint pattern, was developed for each powering section. Attachment of the form tie and developing the forming timber boxes during formwork planning required a particularly high degree of creativity. To connect the outer formwork, the Competence Center fair-faced concrete developed for the first time a special angle railer capable of accommodating the different wall inclination. This solution was required because of high concrete pressure and the geometry of the column. Once formwork planning was completed, the Doka ready-to-use service embarked on pre-assembling the inner and outer formwork for the 5 powering sections. Large area formwork top 50 delivered to the site ready-to-use serves as the base. On site, the formwork was fitted with 18 mm thick multi-layer formwork sheets that were to ensure a special fair-faced concrete result. Top 50 panels on the lateral surfaces were shored up by the load-bearing tower Staxo 100, the timber beam formwork supported by Urex 60 and spindle strut T7. The formwork solution developed by Doka ensured timely and rapid implementation of the complex geometry on site and produced outstanding results.